Hey everyone, for this week's experiment, it will be over molecular models. I will cover electron configuration, principles and rules you should be aware of, Lewis dot structures, Vesper theory and geometries, electronegativity, and polarity. These concepts aren't essential just for this lab. We'll be using these concepts during general chemistry too, as well as organic chemistry. The electron configuration of an atom or molecule is the distribution of its electrons in atomic or molecular orbitals. The orbitals you will need to know is s, p, d, and f, and they each hold 2, 6, 10, or 14 electrons respectively. N is the principal quantum number and is the energy level for the orbitals. As seen in the picture up top, the energy level goes before the type of orbital. To complete the electron configuration, you need to include how many electrons are in each orbital, which will be expressed as an exponent after the type of orbital. The angular momentum quantum number, which is L, determines the shape of the electron's orbital. L ranges in values from 0 to n minus 1. The second picture shows the path when trying to figure out the electron configuration of an atom or molecule. For an example, I will go over the electron configuration of sodium. First, you will have to know how many electrons sodium has. Looking at the periodic table, it has 11. Start with filling the first orbital, 1s2. We have 9 more electrons to go. Now following the path, we will fill the 2s orbital with 2 electrons. Next, fill the 2p orbital. We can place 6 electrons in this orbital since it's the p orbital. Looks like we have 1 more electron to go and we will give it to the 3s orbital. Now it's to combine the orbitals to get the complete electron configuration, which is seen at the bottom of the slide. 1s2, 2s2, 2p6, 3s1. There are principles and rules we need to follow when placing electrons into orbitals. First is the Aufbau's principle. Principle states that electrons will occupy orbitals with the lowest energy first, so we would not be able to fill the 3s orbital before the 1s and 2p orbitals are filled. Next is the Pauli exclusion principle. There is a maximum of 2 electrons with opposite spins that can fit in a subshell of an orbital. For a visual, look at the second visual. There's a correct and incorrect way to place the spins on the electrons. You cannot have the arrows facing the same way. Now let's look into Hund's rule. Hund's rule states that we must fill all subshells of similar energy first before pairing another electron with an opposite spin. Refer to the third visual on the correct and incorrect way of placing electrons into subshells of the orbitals. You can see how the 2p orbital has 3 subshells that can occupy a max of 6 electrons. But for this example, there are only 2 electrons to place. Instead of placing both electrons in the same subshell, you have to distribute at least 1 electron in each subshell before doubling up. We have one more rule to look at, the octet rule. When forming compounds, atoms have the goal to lose, gain, or share electrons to have a total of 8 electrons in their valence shell, resulting in the same electron configuration of a noble gas. They want to reach noble gas configuration because it's the most stable. There are exceptions to this rule though. Molecules with an odd number of valence electrons cannot have its atoms fulfill an octet. Another exception are molecules in which 1 or more atoms possess more than 8 valence electrons, like those who have an energy level greater than 2. Also, molecules in which 1 or more atoms possessing less than 8 electrons. Referencing to the visual, chlorine has 7 electrons but shares its electrons with hydrogen to now fill an octet. Hydrogen is an exception of the octet rule because it possesses less than 8 electrons and has an odd number of electrons. Now, let's move on to how to draw Lewis dot structures. First, you will want to draw the skeletal structure for the molecule. For example, ammonia would be NH3. Next, sum all valence electrons of each atom in the molecule. If the molecule has a charge, always add 1 electron for each negative charge and subtract 1 electron for each positive charge. Now it's time to distribute electrons among the atoms. Connect the terminal atoms to the central atom using single bonds first. Each bond consists of 2 electrons. Then distribute the electrons on the terminal atoms without having them surpass 8 neighboring electrons. If there are remaining electrons, place them as lone pairs. If necessary, form double or triple bonds to give atoms their octet. Finally, check that you have the lowest formal charge possible for all the atoms, using the equation on the slide. Valence shell electron repulsion theory, or VESPER, is used in chemistry to predict the geometry of individual molecules from the number of electron pairs surrounding their central atoms. To predict the geometry of a molecule, you will want to draw a Lewis structure first and count all the neighbors. When counting neighbors, include bonded atoms as well as lone pairs. Now arrange the neighbors to be far away from each other. I will get into repulsion trends soon. Finally, you can establish an electron group shape and molecular shape. In the next slides, you will see a table of VESPER geometries and how to determine the geometry of a molecule based on several aspects. Let's go over the repulsion trends I mentioned earlier. There are two types of valence shell electron pairs, bond pairs and lone pairs. Bond pairs are shared by two atoms and are attracted by two nuclei. Hence, they occupy less space and cause less repulsion. Lone pairs are not involved in bond formation and are in attraction with only one nucleus. Hence, they occupy more space and cause more repulsion. The order of repulsion between different types of electron pairs is as follows: lone pair, then lone pair, then bond pair, bond pair. These next two slides include a comprehensive table of electron and molecular shape geometries. I advise to learn the basic geometries to help you with your lab assignment as well as for future chemistry encounters. This is a continuation of the table showing the VESPER geometries, but this one's with the 5 and 6 electron groups on the central atoms. Next topic is electronegativity. Elements are given electronegativity values to describe their tendency to attract electrons toward themselves. Values increase from left to right and from bottom to top in the periodic table. Fun fact, fluorine is the most electronegative element. Polarity is the distribution of electric charge over atoms joined by a bond. A bond is considered polar when there's a dipole moment present and electrons are not shared equally between atoms. The change in electronegativity values ranges from 0.4 to 2. Non-polar bonds have no dipole moment and electrons are shared equally between atoms. Non-polar molecules like methane that has a chemical formula of CH4 are symmetrical. Change in electronegativity values ranges from 0 to 0.39. Well, that's it for pre-lab lecture for molecular models. Enjoy your lab assignment and stay safe.